Galaxies spin too fast. Something invisible is holding them together. In the 1970s, astronomers began noticing something strange when observing the movement of stars in spiral galaxies. According to traditional physics, stars farther from the center should move more slowly, since they'd be less bound by the gravity of the central mass. But that's not what the telescopes revealed. Distant stars were orbiting at nearly the same speed as those near the center. That seemed impossible unless something invisible was there, holding everything in place. The way these galaxies behaved directly contradicted Newton's laws, which work perfectly for planets and stars on smaller scales. To maintain such high speeds, there would have to be far more mass than what we could see. In other words, either there was an enormous amount of unseen matter, or our physics was wrong. It was like watching a merry-go-round spin faster than its visible supports could handle, yet seeing no hidden cables keeping it together. Vera Rubin, an astronomer dedicated to studying these rotation curves, was among the first to show that this wasn't an isolated case. She measured the rotation speeds of many galaxies and found they all had the same anomaly. The outer stars didn't slow down as expected. Instead, their speed stayed steady, as if an invisible field were holding them in place. This field became known as the dark matter halo. If it had been just one or two galaxies, it would have been easy to blame a calculation error or an unusual configuration. But the pattern was consistent across hundreds, then thousands of galaxies. The traditional model of visible mass simply couldn't explain it. The only possible answer was the presence of an invisible substance spread throughout each galaxy, something that didn't emit light, didn't interact with radiation, but still had gravity. This was the birth of the modern idea of dark matter, a substance we can't see but whose presence is revealed through its gravitational effects. It's like a hidden web giving structure to the cosmos. Without it, galaxies would slowly tear themselves apart, unable to stay bound by visible matter alone. The gravity from stars and gas wasn't enough. Something was missing. Over the decades, new observations confirmed this behavior on even larger scales. Neighboring galaxies were also moving in puzzling ways, hinting at more mass than we could detect. It was as if the universe were covered by an invisible skeleton, dense enough to tie everything together. But when astronomers searched for this extra mass with telescopes, it was nowhere to be found. They considered other possibilities: vast clouds of interstellar gas, rogue planets, black holes, but none of them added up to enough. Even including every known source of invisible matter, more than 80% of the required mass was still missing. The evidence was overwhelming, but deeply frustrating. We knew dark matter had to be there, we just didn't know what it was made of, or even if it was matter in the traditional sense. Galaxies spinning too fast became one of the central mysteries of modern astronomy. Without dark matter, the current structure of the universe simply wouldn't make sense. Galaxies would have flown apart shortly after forming. That's why dark matter went from a fringe idea to a cornerstone of cosmology. The universe was telling us something. We just didn't know how to listen. The implications are profound. We're talking about a substance that, while invisible, makes up about 27% of everything that exists. The matter that forms stars, planets, and people, so-called normal matter, accounts for only 5%. The rest, aside from dark matter, is dark energy. In other words, the vast majority of the universe is something we can't see, touch, or measure directly. We live surrounded by the unknown. This changes how we think about the cosmos. What we see is only a fraction of the whole, and that fraction is the part that interacts with light. The rest, the overwhelming majority, works silently in the background. It shapes the fate of galaxies without ever shining. It's like trying to understand an entire play while only seeing the curtain. Modern physics has had to embrace this emptiness. The standard cosmological model, called lambda CDM, takes dark matter as a fundamental ingredient. Without it, simulations don't work. Galaxies don't form. The universe's large-scale structure doesn't appear. Dark matter is like the invisible glue of reality, and yet we still don't know what it's made of. That's the central irony. The more science advances, the more we run into the invisible. The cosmos offers clues through the movement of stars, rotation curves, and the distribution of mass. But we can't crack the true nature of this entity. All we know is that it's there, always present, always out of direct reach. And that's why this story is far from over. The enigma Vera Rubin discovered and no one could refute. Vera Rubin wasn't just an observational astronomer. She was a challenger of certainties. At a time when astrophysics was dominated by men and rigid ideas, she looked at galaxies with a persistent doubt. Why didn't the data match the theory? What seemed like a small statistical error revealed a conceptual abyss. Rubin didn't find a mistake, she found a new universe. Her research focused on something specific: galactic rotation curves. It was expected that star velocities would decrease with distance from the center, as happens with planets in the solar system. But what Rubin observed was the opposite. The velocity remained constant, regardless of distance. This directly contradicted classical gravity. It was as if something invisible was interfering. At first, her discovery was met with skepticism. Many thought the data was wrong, or that it was some kind of optical illusion, instrumental distortion, or calibration error. But Rubin was meticulous. She repeated the tests, used different telescopes, analyzed different galaxies, and the pattern persisted. Classical physics couldn't explain what she saw, and no one could prove her wrong. Over time, Rubin's data began to accumulate. Dozens, then hundreds of galaxies displayed the same signature: flat rotation curves. This required much more mass than what was observable. The most reasonable hypothesis was the existence of a halo of invisible matter surrounding each galaxy. Rubin was unintentionally uncovering one of the greatest enigmas of the universe. It's important to note, Rubin wasn't looking for dark matter. She simply followed the data with intellectual honesty. That made her discovery even more powerful. The evidence didn't come from speculative theory, but from direct observation. The universe was shouting for attention, and Rubin was the first to hear it clearly. Her contribution changed cosmology forever. Before her, dark matter was just a fringe hypothesis, occasionally used to explain isolated discrepancies. After her, it became an unavoidable part of any model that took the data seriously. Science had to admit that more than 80% of the universe's mass was hidden. Despite this, Rubin never won the Nobel Prize, which many consider a historical injustice. Her discovery is as impactful as the expansion of the universe or the cosmic microwave background. She was the one who turned mystery into evidence. Her humility and scientific rigor left a deep legacy, and her presence still echoes in today's research. Today, modern telescopes, computer simulations, and detection experiments continue to try to understand what Rubin unearthed. Every measured rotation curve reinforces the mystery. Every attempt at refutation ends up strengthening the hypothesis. The cosmos seems to conspire in favor of the idea that we are surrounded by something we cannot see. But even with all this gravitational evidence, we still haven't directly detected a single dark matter particle. This makes Rubin's legacy even more unsettling. She didn't give us the answer, she gave us the right question. And sometimes that's more powerful than any explanation. Rubin's story also reveals something about the scientific method. Progress doesn't always come from the most elegant theory, but from persistence in the face of uncomfortable data. It takes courage to say, "This doesn't make sense," when everyone else says it does. Vera Rubin had that courage and changed astronomy forever. At the end of her life, Rubin said that the universe was mostly made of things she didn't understand. That phrase, spoken simply, carries the essence of true science. It reminds us that the unknown is not a failure, but a frontier, and that every time we uncover a little more, we reveal how much we still don't know. Galactic clusters that should fall apart but don't. Far beyond individual galaxies, there is an even larger structure: galaxy clusters. They are like cosmic archipelagos, with hundreds or even thousands of galaxies orbiting a common center of mass. But when astronomers calculated the total visible mass of these clusters, something didn't add up. Gravity seemed too weak to keep so many galaxies bound together. In practice, they should have dispersed over time. The first to notice this problem was Fritz Zwicky in 1933, while studying the Coma cluster. He compared the velocity of the galaxies to the total mass that could be measured by the emitted light. The numbers didn't match. There was far less visible matter than needed to keep the cluster cohesive. Zwicky called this invisible material dark matter. At the time, the scientific community ignored him. Decades later, Vera Rubin's observations of individual galaxies breathed new life into Zwicky's hypothesis, and then clusters returned to the spotlight. Modern measurements confirmed it. Even adding up all the stars, hot gas, and cosmic dust, the total visible mass was only a fraction of what was needed. Yet the clusters remained stable for billions of years. The question became inevitable: what was holding them together? The most powerful evidence came from light, or rather from the distortion of light. Galaxy clusters act like giant gravitational lenses, distorting the light of objects behind them. The strength of this distortion allows scientists to estimate the total mass involved, and once again, the result was clear. There was much more gravity than visible matter. It was as if the clusters were surrounded by gigantic, invisible halos. These halos, made of dark matter, seemed to form a kind of invisible mesh across the universe. They not only kept the galaxies bound within clusters, but also connected clusters to one another through cosmic filaments. These filaments form what scientists call the cosmic web, a colossal structure that shapes the universe on a colossal scale. And it is made, for the most part, of something we cannot see. The hot gas between galaxies also reinforces the mystery. It emits X-rays detectable by space telescopes, but even this additional mass is still not enough. Galaxies should escape the cluster's gravity if we accounted only for visible matter and gas. Once again, the only explanation that holds is the dominant presence of dark matter. One of the great advantages of clusters is that they provide multiple independent ways of measuring mass. It's possible to estimate it by the velocity of galaxies, by the X-ray emissions from the gas, and through gravitational lensing. And all these approaches point to the same verdict: there is much more mass than we can detect with light, and it is distributed in a way that ensures the stability of the system. This convergence between independent methods makes the evidence almost indisputable. It is no longer a localized inference, but a universal pattern. Dark matter is not a localized anomaly. It is everywhere, supporting the architecture of the universe across multiple scales. Galaxy clusters are like giant monuments to its presence. Cosmological simulations also confirm this scenario. When scientists try to recreate the formation of clusters using only visible matter, the result is disappointing. The systems don't form, or they disintegrate quickly. But when dark matter is included in the equations, clusters naturally emerge and remain stable for billions of years. The simulation matches what we observe. Curiously, clusters also tell us that dark matter cannot be something that interacts strongly with normal matter. If it did, we would see side effects such as collisions or energy emissions. But the halos of dark matter seem to pass through each other like ghosts, influencing only through gravity. This further limits the possible natures of the substance. One of the most famous examples is the bullet cluster, where two colossal masses collided. Data showed that the normal matter, hot gas, lagged behind after the impact, while gravity moved ahead, following the dark matter. This provided an indirect photograph of the separation between visible and dark matter. An accidental cosmic experiment, but a highly revealing one. Galaxy clusters therefore function as natural laboratories. They not only reinforce the need for dark matter, but also help us narrow down its properties. They show that it is not luminous, not noisy, not interactive in the usual sense, but it is powerful. Its gravity shapes the largest objects in the cosmos, and it remains an inescapable presence, even if untouchable. When light bends where there's nothing, the lensing of the invisible. In the depths of space, something strange happens to light. As it travels through the universe, it sometimes bends, not because it hits an object, but because space itself is warped. This bending, known as gravitational lensing, was predicted by Einstein's theory of general relativity. Massive objects, like galaxies and clusters, curve spacetime, altering the path of light. But in many cases, we see light bending around nothing. Astronomers started noticing lensing effects where visible mass simply couldn't explain the distortion. Galaxies in the background appeared stretched, warped, or duplicated, clear signs of strong gravitational influence. Yet the visible matter nearby wasn't enough to cause such dramatic effects. It was as if something invisible was acting as a lens, warping the fabric of spacetime in silence. This invisible lens had a name: dark matter. Gravitational lensing became one of the most powerful tools to map dark matter. Unlike other techniques, it doesn't rely on detecting light or particles. It simply observes how light behaves around massive regions. And time after time, the pattern holds. There's more mass than we can see. The lensing tells a story of structure, gravity, and mass, even when our instruments detect only darkness. There are two types of lensing, strong and weak. Strong lensing causes dramatic arcs and multiple images of the same galaxy. Weak lensing, more subtle, shows up as slight distortions across thousands of galaxies. When astronomers stack these tiny distortions statistically, they reveal large-scale maps of hidden mass. These maps show that dark matter isn't randomly scattered. It forms patterns, filaments, halos. One of the most iconic examples is the bullet cluster. Two galaxy clusters collided, and the resulting image gave a cosmic X-ray of the event. The visible matter, mostly gas, lagged behind the collision due to friction. But the gravitational lensing revealed that the bulk of the mass had moved forward with the galaxies. This mismatch showed that most of the mass isn't in the gas, but in invisible dark matter halos. The bullet cluster provided one of the clearest pieces of evidence separating dark matter from normal matter. It showed that dark matter doesn't interact much, even during violent cosmic events. It passes through like a ghost, affecting only gravity. This behavior is incompatible with theories that try to explain dark matter as a misinterpretation of gravity. Something real, massive, and invisible is there. What makes lensing so elegant is its neutrality. It doesn't care what dark matter is made of. It just shows where gravity is strongest. Whether dark matter is a particle, a field, or a complete paradigm shift, Lensing reveals its fingerprints. Every distorted galaxy in the background is a clue. Every warped arc tells us where the unseen matter lies. Recent space telescopes like Hubble and Euclid have taken this to new levels. They've mapped dark matter on cosmic scales, revealing a vast network of invisible filaments connecting galaxies and clusters. These filaments follow the same cosmic web structure predicted by simulations. It's as if we're seeing the skeleton of the universe, illuminated only by the way it bends light. Without dark matter, the lensing data makes no sense. The distortions would be far weaker, the patterns would not align, and the underlying structure would fall apart. But with dark matter included, everything fits. The mathematics, the observations, the simulations, they all align. It's one of the rare cases where an invisible theory becomes visible through its consequences. Gravitational lensing is also helping probe the properties of dark matter. By comparing how it clumps, how dense the halos are, and how fast structures form, we can narrow down possible models. It's a bit like fingerprinting a suspect we've never seen, using only shadows and effects. Yet the accuracy keeps improving, and the mystery keeps getting sharper. Some have proposed alternative explanations like modified gravity or extra dimensions, but none explain the full range of lensing phenomena. The bullet cluster alone invalidates many of them. We may still not know what dark matter is, but lensing shows us where it lives, and that it's real. That invisible hand shaping the cosmos isn't just theory. It bends light. It builds the universe. Dark matter, the invisible architect of every galaxy. Galaxies are not random. Their structure, shape, and stability follow hidden rules, rules shaped not by what we see, but by what we don't. Stars alone can't explain why galaxies hold together, nor can gas, dust, or black holes. Something else is responsible for shaping the skeleton of every spiral, every cluster, every elliptical giant. That something is dark matter. Computer simulations offer a unique window into this invisible architecture. When we model the early universe with only visible matter, galaxies fail to form. Structures collapse too slowly or disperse. But when dark matter is included, everything changes. Galaxies emerge naturally from tiny ripples in the early universe, drawn together by the gravity of invisible halos. These halos form first, long before any star is born. They're like scaffolding, pulling in gas and dust that eventually cools and ignites into stars. Without the dark matter halo, there's no frame to catch the raw materials. The visible galaxy is just a luminous decoration on a far larger, darker structure. In this model, dark matter isn't a detail, it's the foundation. Each galaxy sits at the center of a vast, roughly spherical halo of dark matter. These halos are massive, often 10 times heavier than the visible part of the galaxy. They extend far beyond the last visible stars, like a silent cocoon of gravity. And they don't just hold the galaxy together, they guide its evolution, its mergers, its shape, its destiny. The shape of dark matter halos also matters. Some are smooth and round, others are clumpy, filled with subhalos. These clumps can affect how stars move, how spiral arms form, and how galaxies collide. The halos also merge with one another, triggering galactic collisions that reshape entire systems. Every movement is choreographed by an invisible gravitational field. Simulations like the Millennium and Illustris projects have visualized this in stunning detail. Starting from basic physics and dark matter, they recreate the cosmic web and the birth of galaxies. The results match what we see through telescopes: clusters, filaments, voids. It's a powerful argument that dark matter isn't just theoretical, it's predictive. It builds structure. Even satellite galaxies are influenced by dark matter. The Milky Way, for example, has dozens of tiny companions. Their distribution and behavior make more sense when embedded in our galaxy's dark matter halo. Some move too fast to be bound by visible matter alone. Others seem mysteriously stable. In both cases, the halo explains what stars cannot. Dark matter also helps resolve long-standing puzzles. For example, why do galaxies rotate with such surprising stability? Why do they survive collisions? Why do their outer regions behave as if they have more mass than they show? The dark matter halo answers all of these, not just qualitatively, but with measurable precision. It's the hidden infrastructure. Interestingly, not all galaxies show the same dependence. Some rare ultra-diffuse galaxies appear to lack dark matter entirely. These outliers puzzle scientists. Are they exceptions that prove the rule or evidence of a gap in our model? In either case, the vast majority of galaxies follow the same dark pattern. Invisible halos first, stars later. The idea that galaxies are decorations on dark matter scaffolds flips our understanding of cosmic architecture. What we admire, the glowing arms, the bright cores, the dazzling nebulae, are secondary. The real builder, the one who laid the groundwork, remains unseen. It's like studying a building and realizing the beauty is supported by hidden steel beams. Future instruments, like the Vera Rubin Observatory, named after the very woman who revealed this mystery, will map millions of galaxies and their dark skeletons. As our resolution sharpens, we may even begin to see variations in dark matter behavior, hints of its true nature. Until then, we know this much. Dark matter didn't just shape galaxies, it made them possible. Everything you think is matter probably isn't. When we think of matter, we imagine things we can touch: rocks, air, people, stars. But in the cosmic scale, this familiar matter, called baryonic matter, is a tiny fraction of what exists. The atoms that form your body and everything you see make up less than 5% of the universe. The rest is something else entirely. Most of what holds the universe together is not like us. The term dark matter doesn't just refer to unseen objects. It refers to a form of mass that doesn't emit, absorb, or reflect light, and doesn't behave like normal matter. It's not made of protons, neutrons, or electrons. It doesn't clump into stars or planets. It's invisible to telescopes and immune to most forces except gravity. It's as if the universe had a second kind of substance, one that stays hidden. Scientists first tried to explain away dark matter as just ordinary stuff that's hard to see: dim stars, brown dwarfs, black holes, or gas clouds. But even if you add up all of these, the mass still doesn't come close. Observations from galaxy rotations, gravitational lensing, and cosmic microwave background measurements all demand far more mass than these faint objects can offer. The gap is too big. It's like trying to weigh a bridge by adding up all the visible cables and beams, only to find you're missing 80% of the mass. Something else is carrying the weight, and it's not made of steel. That's what scientists are up against. The standard model of physics accounts for the matter we know, but dark matter doesn't fit into it. It's outside the known list of particles. To complicate things further, dark matter doesn't clump on small scales the way regular matter does. It doesn't form planets or light up like stars. It spreads out in diffuse halos surrounding galaxies and clusters. This smooth, large-scale behavior helps hold cosmic structures together, but makes detection incredibly difficult. It's everywhere and nowhere at once. When astronomers simulate the early universe, they include both baryonic matter and dark matter. Without the dark component, galaxies don't form correctly. Stars don't group as they should. the web of the universe collapses or never grows. The existence of dark matter is not just a patch, it's a foundation. Without it, we wouldn't be here. The cosmic microwave background, the afterglow of the Big Bang, also supports this. Its tiny fluctuations, mapped in exquisite detail by missions like Planck and WMAP, match predictions that include dark matter. These fluctuations gave rise to the first galaxies, and their patterns require an invisible mass to make sense. Light alone can't explain the early universe's structure. Even the way galaxies move inside clusters demands dark matter. Their speeds suggest gravitational pulls far beyond what visible mass can produce. This is not a small discrepancy. It's off by a factor of 5 or more. The only way to make the math work is to admit what we see is not all that is. Most matter is not atoms. It's something else. And yet, this something else refuses to reveal itself in labs. Particle accelerators, detectors buried underground, telescopes scanning the cosmos, all have failed to catch it in the act. It's not just hard to find, it may not interact in any way we're used to. It may pass through your body right now undetected, like neutrinos, only even more elusive. The irony is profound. Physics, a field built on the tangible and measurable, is now led by shadows and silence. The world we understand is a surface. Underneath it lies a deeper reality, composed of unknown matter. And every time we learn more about galaxies, clusters, and the cosmos, that shadow world grows clearer, even as it remains untouchable. This challenges how we define existence. If something doesn't emit light, doesn't interact, and can't be directly measured, but still shapes galaxies, is it any less real? Dark matter rewrites what we mean by stuff. It asks us to expand our senses and our theories beyond the visible, because clearly the universe doesn't care whether we can see its secrets. In the end, most of what you think is matter, stars, gas, people, planets, is not representative of the cosmos. It's a tiny exception. The rule is dark, cold, and silent. We are built from cosmic leftovers. The real mass of the universe is made of something else entirely. WIMPs, axions, and ghost particles, the zoo of the hidden cosmos. If dark matter exists, and all evidence says it does, then it must be made of something. But what? That simple question has sparked one of the most expansive hunts in physics. Since dark matter doesn't match any known particle, scientists have created an entire zoo of hypothetical candidates, each one stranger than the last. Welcome to the realm of WIMPs, axions, and ghost particles. WIMPs, or weakly interacting massive particles, are the most famous contenders. They would be heavy, slow-moving particles that rarely interact with normal matter, hence weakly interacting. If WIMPs exist, trillions could pass through your body every second without you feeling a thing. Their mass would give them gravitational pull, allowing them to form halos around galaxies. But so far, no WIMP has been found. Experiments like Lux, Xenon, and Panda X have tried to detect them. These ultra-sensitive detectors are placed deep underground, shielded from cosmic radiation, waiting for the rare moment when a WIMP might hit a nucleus. Decades of searching, however, have produced only silence. The deeper we look, the quieter it gets. WIMPs may not exist, or they may be even more elusive than we thought. Another contender is the axion, a lightweight, nearly massless particle proposed to solve problems in quantum physics. Axions wouldn't act like WIMPs, they'd be produced in vast numbers, forming a cold, invisible fog across the universe. They'd interact so weakly with normal matter that their detection requires entirely different approaches. Telescopes, resonant cavities, even neutron stars have been proposed as ways to catch them. Then there are sterile neutrinos. Unlike regular neutrinos, which barely interact but still leave traces, sterile neutrinos wouldn't interact via any force except gravity. They'd be like shadows of shadows. Some observations, like unexplained X-ray emissions from galaxy clusters, have been suggested as hints of their decay. But again, no confirmation, just tantalizing whispers in the noise. Some theories go even further. What if dark matter is not a particle at all, but a field, a new kind of physics that manifests only on large scales? Others suggest dark sectors, entire families of particles and forces hidden from our universe, interacting only through gravity. These shadow worlds might contain their own chemistry, their own dynamics, completely cut off from ours. Supersymmetry once held promise. It proposed that every known particle has a heavier superpartner, and one of those could be dark matter. But as particle accelerators like the Large Hadron Collider failed to find supersymmetric particles, confidence in this idea began to fade. Still, the door remains slightly open. Maybe we've just not looked in the right energy range. Some exotic ideas propose that dark matter might not be evenly distributed. Maybe it clumps into massive dark stars or creates dense objects like black halos. Perhaps it even formed the seeds of supermassive black holes at the centers of galaxies. If so, dark matter wouldn't just shape galaxies, it would have sculpted the entire cosmic timeline. A newer class of candidates includes ultralight dark matter, made of particles with masses trillions of times smaller than electrons. These particles would behave more like waves than particles, spreading out over entire galaxies. Their wave-like nature could explain certain behaviors in galaxy cores that WIMPs can't. It's an elegant model, but remains speculative. What makes this zoo of particles so dizzying is that none of them have left solid tracks. Each theory fills a gap in our understanding. Each candidate offers a different cosmic behavior. Yet the silence from detectors persists. It's like chasing a shadow that shifts every time we build a new flashlight. Every model advances the hunt, but none provide the catch. Despite the silence, the search continues. New instruments, new theories, new patience. The mystery is too deep to ignore. Dark matter shapes galaxies, drives structure, and defines the universe. Its nature may not be in any single particle. It may require rewriting what we think particles even are. Whatever dark matter turns out to be, one particle or an entire hidden sector, it's clear that the cosmos is not built only from what we know. The known universe is just one page in a larger book, and most of the story is still missing. Ultra-precise detectors that hear only cosmic silence. If dark matter is real, and all astrophysical data screams that it is, why haven't we found even a trace of it? For decades, scientists have built incredibly sensitive detectors, some placed in remote underground labs shielded from every imaginable interference. These instruments are designed to catch the briefest, rarest interaction between a dark matter particle and an atomic nucleus. But after billions invested and years of waiting, the detectors remain quiet. One of the most famous examples is the xenon experiment, located beneath a mountain in Italy. Inside, a large tank of ultra-pure liquid xenon sits in complete darkness, waiting. If a dark matter particle collides with a xenon atom, the impact would cause a tiny flash of light. Detectors would pick it up, measure its energy, and mark it as a possible candidate. But flash after flash has been ruled out. Nothing conclusive ever appears. Other detectors follow the same design logic. noble gases, cryogenic temperatures, layers of shielding. Lux, Pandax, and the more recent Lex Zeppelin experiment are all built to push the detection threshold further. Each claims higher sensitivity than the last, yet the story doesn't change. The noise floor drops, the sensors improve, and still, no signal rises from the dark. These detectors are placed deep underground for a reason. Cosmic rays constantly bombard Earth, creating background noise that can mimic a real signal. By going deep into the Earth, often in abandoned mines, scientists reduce this interference. They also use multiple layers of shielding, lead, water, polyethylene, to block natural radiation. In these quietest places on Earth, the universe says nothing. But the silence might not mean dark matter isn't there. It may just mean we're asking the wrong question. What if the particles don't interact at all with atomic nuclei? What if they only interact via gravity or through unknown forces we haven't even conceived? These detectors assume a WIMP-like particle, but if dark matter isn't a WIMP, then they're searching for a ghost with the wrong tools. Some physicists compare it to fishing with the wrong net. You cast into the ocean expecting a particular size and shape, but what if your target swims in a different layer or slips through the mesh? The ocean is still full of life, but your method blinds you to it. That's the frustration and the challenge of dark matter detection. We may be exquisitely tuned to the wrong frequency. Occasionally, a detector picks up an anomaly, a tiny blip that doesn't match background noise. The scientific world holds its breath, hoping it's finally the signal we've waited for. But each time, follow-up analysis rules it out. A technical glitch, a stray neutron, a miscalibration. The silence returns, the tension builds, the hunt continues. Meanwhile, the detectors themselves keep evolving. New generations are larger, colder, quieter. Some use cryogenic crystals, others rely on superconducting sensors. A few are looking beyond direct detection, searching instead for hints of dark matter annihilation or decay in the cosmos. We're no longer betting on a single method, but on a global, multi-pronged search. These ultra-sensitive machines are marvels of engineering. They operate near absolute zero, detect single photons, and filter data with extreme precision. But their greatest feature is also their most haunting: their ability to measure nothing. For decades, they've offered the cleanest, most confident non-detections in physics. The silence is deafening and scientifically priceless. Why? Because each failed detection rules out part of the possible landscape. We now know dark matter doesn't interact above a certain cross-section. We've narrowed down its mass range. We've eliminated models that once seemed likely. The silence is slowly sculpting the boundary of truth. It's frustrating, but it's progress. Still, the lack of interaction has left some physicists uneasy. What if we've built cathedrals to detect a phantom? What if dark matter isn't a particle at all, but a shift in gravity's behavior, or a hidden dimension, or something we haven't even imagined? In that case, these detectors are not wrong, just incomplete. Until then, they keep listening. Every day, every second, in the darkest, coldest rooms on Earth, machines sit in silence, waiting for a whisper from the invisible. So far, the only thing they've heard is the absence of an answer. But sometimes, silence is just the beginning of a deeper discovery. Underground tunnels, chasing what cannot be seen. Deep beneath mountains and frozen landscapes, humans are building temples to the unseen. These are not mines for gold or oil. They are cathedrals of silence, carved to detect something that refuses to show itself: dark matter. Why underground? Because only in these shielded voids can we escape the noise of the surface and listen for interactions that are impossibly rare. Welcome to the world beneath the world. The Gran Sasso Laboratory in Italy lies beneath 1,400 meters of rock. SNO Lab in Canada sits inside an active nickel mine. China's CJPL burrows through mountains to reach the Earth's deepest experimental hall. These places are shielded from cosmic rays and radiation, forming quiet zones where detectors can wait for years for a single possible signal. They are cleaner than hospital rooms, colder than Antarctica, darker than space. Every detail is designed for silence. Scientists wear special suits to avoid contaminating the detectors. Air is filtered, floors are dust-free, and even static electricity is controlled. Any stray particle, vibration, or radiation could mimic a dark matter event, so the environment must be perfectly still. It's like trying to hear a whisper in a thunderstorm. These tunnels create the silence needed for that whisper to reach us. What's being hunted isn't just invisible, it may not even interact with the matter we know. Yet billions are spent building multi-ton machines in these silent tombs, in hopes of detecting the unseeable. It's a paradoxical pursuit, chasing particles we don't know how to catch, with tools built from theories we hope are right. But the alternative, doing nothing, would be a failure of imagination. Some of these detectors use liquid xenon, others use crystals cooled to near absolute zero. Some rely on ionization, others on faint flashes of light. All share one goal: capture an interaction, however fleeting, between dark matter and a nucleus. The hoped-for event would be incredibly rare, maybe once a year, maybe once a century. That's why the tunnels must be so deep and the wait so long. The isolation also brings unique challenges. Maintenance becomes complex. Equipment failures must be fixed with minimal intrusion. Power systems must run flawlessly. Data must be constantly filtered, checked, and analyzed. And the scientists? They work in rotations, entering these underground sanctuaries for shifts that feel more like space missions than lab work. It's science at the edge of human patience. There's something poetic about the contrast. Massive structures built to detect something that might not exist. Human ambition drilling into bedrock, hoping to find a shadow that bends galaxies. It's not unlike ancient explorers chasing monsters at the edge of maps. Only now the maps are cosmological, the monsters are theoretical, and the oceans are made of gravity. But these tunnels have other uses too. They help test fundamental physics, neutrino behavior, proton decay, and even rare radioactive processes. Their extreme silence allows multiple experiments to run in parallel. While waiting for dark matter, these labs contribute to other breakthroughs. The darkness breeds unexpected insights. Every tunnel is also a message, a declaration that we haven't given up on the unknown. Each lab is a monument to curiosity, precision, and patience. Whether they find dark matter or not, they are reshaping how we do science, moving from the stars to the depths, chasing the invisible by listening to the void. In recent years, new proposals have emerged: larger detectors, deeper tunnels, more advanced shielding. The dark side experiment, Darwin, and others promise unprecedented sensitivity. Some even suggest going beneath the ocean floor. If dark matter hides deeper, we will follow. The chase goes on. And maybe one day, the silence will break. A faint signal will rise above the noise. One flash, one vibration, one deviation from the expected. That's all it takes. A single event could rewrite physics from the quietest place on Earth. Until then, the tunnels remain, always listening, always waiting. Does dark matter talk to itself? Maybe. For decades, scientists believed dark matter was completely silent, interacting only through gravity. It didn't collide, clump, or radiate. It passed through itself and everything else like a ghost. But new observations suggest that might not be the whole story. What if dark matter isn't entirely antisocial? What if, under the right conditions, it talks to itself? This idea, called self-interacting dark matter, proposes that dark matter particles may occasionally bounce off one another. Not strongly, not often, but enough to change how dark matter behaves in dense environments. This could help explain puzzling features in galaxies that standard dark matter models struggle with, especially in the crowded centers of galaxies where something doesn't quite add up. Take dwarf galaxies, for example. Their dark matter cores seem too puffy, less dense than expected. Standard cold dark matter predicts sharp central peaks in density, but observations show flattened cores. If dark matter particles occasionally nudge each other, they could redistribute energy and soften these central regions. That would match what we see, without rewriting gravity. Another clue comes from colliding galaxy clusters. In some cases, the visible matter lags behind, while the dark matter, mapped by gravitational lensing, behaves oddly. If dark matter self-interacts, it might slow down slightly or scatter during collisions, just like regular matter does. This opens up the possibility of measuring its internal friction, giving us insight into its physical nature. Models of self-interacting dark matter are still highly speculative. They require new particles and forces beyond the standard model, but they offer a way to reconcile small-scale discrepancies without throwing away the successes of large-scale simulations. It's not a rejection of cold dark matter, it's an evolution, a fine-tuning, a whisper of complexity beneath the silence. Some versions of this theory even suggest a hidden force, like an invisible version of electromagnetism. In this view, dark matter could form atoms, plasma, or even dark radiation, a whole shadow world with its own physics, invisible to us except through gravity. If true, we're not just missing particles, we're missing an entire parallel sector of the universe. The catch is that self-interaction must be rare. Too frequent, and galaxies would lose their structure. Too infrequent, and nothing would change. The sweet spot is hard to find and even harder to prove. Experiments must combine astrophysical observations with detailed simulations, searching for subtle deviations in how galaxies behave. Observations from the Hubble Space Telescope and Chandra X-ray Observatory have been used to test these ideas. By comparing the positions of dark matter and hot gas in colliding clusters, scientists can estimate interaction rates. So far, results are inconclusive. Some clusters suggest interaction, others don't. The signal is faint, the picture incomplete. But the idea has traction. It shows that dark matter might be more than just a mass placeholder. It could have structure, rules, and internal dynamics. It could respond to its environment, not just impose gravity on it. This would mark a shift in how we search, what we expect to find, and how we model the universe. Theorists have even built simulations with self-interacting dark matter. The results are promising. More realistic galaxy cores, better matches with satellite galaxy distributions, and smoother evolution. But again, these are simulations. Until direct evidence emerges, the theory remains intriguing but unconfirmed, a possibility waiting in the dark. Self-interaction could also help us explain anomalies in gravitational lensing, galaxy rotation curves, and even dark matter distribution around supermassive black holes. If these particles interact, even weakly, it would drastically change our approach. New detectors, new assumptions, new strategies. Maybe dark matter isn't entirely silent. Maybe it whispers in a language we haven't yet learned to hear. And maybe, just maybe, the silence we thought was total is filled with hidden conversations. Cold, hot, or warm, the temperature of dark matter. Not all dark matter is the same, or at least not all theories agree on how it should behave. One key difference lies in temperature. Not the kind you measure with a thermometer, but a metaphor for how fast the particles move. The temperature of dark matter shapes how it clumps, how it spreads, and how galaxies form. In cosmology, it's all about cold, hot, or warm. Cold dark matter, CDM, is the dominant model. It assumes dark matter particles move slowly, almost sluggishly, in the early universe. Because of this, they clump together easily, forming dense halos. These halos become the scaffolding for galaxies and clusters. The CDM model explains large-scale structure very well, from the cosmic web to galaxy clusters. But CDM has problems on smaller scales. It predicts too many small satellite galaxies around the Milky Way. It also suggests denser galaxy cores than we observe. These discrepancies have led scientists to explore alternatives. That's where hot and warm dark matter come in. They offer different moods of the invisible mass, more kinetic, more spread out. Hot dark matter consists of fast-moving particles, so fast they wipe out small structures as they zip through space. Neutrinos are a real-world example of this. They barely interact and move at nearly the speed of light. But hot dark matter doesn't work well for structure formation. It erases too much detail. The cosmic web falls apart. So it's largely ruled out as the main form of dark matter. Warm dark matter is a middle ground. Particles are lighter and faster than cold dark matter, but slower than neutrinos. They suppress small structures without destroying everything. Simulations with warm dark matter produce fewer satellite galaxies and smoother cores, closer to what we observe. It's a compromise that might reflect reality better than extremes. The difference in temperament affects everything. Cold dark matter leads to lots of small clumps, even in places where we don't see galaxies. Warm dark matter smooths out the small-scale chaos. This changes the number and distribution of galaxies, the way halos merge, and the shape of galactic cores. It's not just temperature, it's architecture. To test these ideas, astronomers study the Lyman alpha forest, a pattern of absorption lines in the spectra of distant quasars. These lines trace the distribution of matter in the early universe. Cold and warm dark matter leave different fingerprints in this forest. It's one of the most precise methods to distinguish between them. The forest holds clues to the temperament of the dark. Another test comes from galaxy surveys. By counting satellite galaxies and mapping dark matter halos, we can compare models. If we see fewer small halos than predicted by CDM, that favors warm dark matter. If galaxy cores are smoother than expected, again, warm models fit better. But data is messy. Nature doesn't hand us clean comparisons. There's also the issue of detection. If dark matter is warm, the particles may be lighter and harder to detect directly. Their interactions could be even weaker than WIMPs. Some models suggest sterile neutrinos as a warm candidate. Others point to ultralight particles with strange quantum behavior. The possibilities are many and frustratingly elusive. Ultimately, the universe may not care about our categories. It could be a mix, mostly cold, with a warm component, or something else entirely, with behavior that doesn't map neatly onto temperature at all. Our terms, cold, warm, hot, may just be placeholders for deeper physics we haven't uncovered. But for now, understanding the mood of dark matter helps narrow the search. It guides simulations, shapes telescope surveys, and defines what signals we should be looking for. Because to catch something invisible, you first need to know how it moves. And in the cosmos, movement reveals the hidden story. Whether sluggish or swift, dark matter has left trails across the universe, and decoding its temperament might be the key to unlocking what it really is. What if gravity is the problem, not dark matter? For decades, astronomers have tried to make sense of missing mass by adding something new, dark matter. But there's another possibility. Maybe we don't need new matter. Maybe we need new gravity. What if our understanding of gravity itself breaks down on large scales? This idea may sound radical, but it has deep roots in the scientific method. When predictions fail, revisit the fundamentals. Isaac Newton's law of gravity works beautifully for apples, moons, and planets, but it was never tested on galactic scales. When stars at the edge of galaxies rotate too fast, one option is to add invisible mass. The other is to change the law. Could it be that gravity weakens less than expected over vast distances? Could it have a hidden side we haven't yet uncovered? General relativity, Einstein's great theory, extends Newton's ideas and explains gravitational lensing, black holes, and the expansion of the universe. But even it has limits. It doesn't include quantum effects. It assumes the vacuum has no structure. And crucially, it predicts the need for dark matter to explain cosmic structures, unless it too is missing something. This line of thought gave rise to modified gravity theories. Instead of adding new matter, we adjust how gravity behaves in weak fields. Maybe gravity gets stronger at low accelerations. Maybe it couples differently with space or time. These ideas sound exotic, but they aim to explain the same data, without invoking invisible particles we can't detect. Some versions even try to unify gravity with other forces or introduce new fields that influence space-time. These modified models aren't just philosophical exercises, they make real predictions. Some match observations of galaxy rotation, lensing, and large-scale structure. Others struggle to reproduce the fine details. But all ask the same core question: are we misunderstanding gravity? The challenge is that gravity is tested mainly within our solar system. Planetary orbits, satellite motion, and lunar laser ranging all confirm Newton and Einstein. But galaxies are another scale entirely, with much weaker fields and more chaotic dynamics. Modified gravity theories argue that what works in the solar system may not apply cleanly to the cosmos. One key advantage of modifying gravity is parsimony. We avoid inventing unseen matter. We deal only with what we already observe. It's a cleaner solution, if it works. But this path comes with risks. Tweaking gravity in one context often breaks it in another. A model that explains galaxy rotation might fail to predict gravitational lensing correctly. To test these ideas, scientists run cosmological simulations using modified laws. They compare the results to real data: galaxy distributions, cosmic microwave background patterns, and gravitational lensing maps. Some models do surprisingly well, others fall apart quickly. The universe, it seems, resists being tricked. It gives up clues, but not the full answer. One of the main difficulties is matching all scales at once. Dark matter fits galaxy clusters, gravitational lensing, and the early universe all at once, even if we don't know what it is. Modified gravity tends to fit galaxies, but struggles elsewhere. Still, some theorists believe it's only a matter of refinement. Perhaps a hybrid theory is needed. The idea that gravity might be incomplete is not unscientific. It's part of the tradition of physics. Newton replaced Aristotle, Einstein replaced Newton, and now maybe something replaces Einstein. But any contender must pass every test, and so far none have succeeded fully. Still, the suspicion lingers. The universe behaves oddly, and gravity is the culprit in the equations. Modified gravity theories are not yet mainstream, but they're not fringe either. They serve as a constant reminder we might be wrong. The success of dark matter models make them dominant, but alternative gravity remains a quiet challenger, waiting for a crack to widen. In science, even long shots get a chance, if they predict something new. For now, the balance leans toward dark matter, but gravity's behavior on large scales is not settled. It may hold surprises. Until we fully understand the force that binds the cosmos, the question remains open. Are we chasing ghosts or just misreading the rules? MOND, the theory that almost explains everything but slips on the details. In the late 1970s, physicist Mordechai Milgram proposed a bold alternative to dark matter. Maybe gravity behaves differently when it gets extremely weak. He called it MOND, Modified Newtonian Dynamics. Instead of adding invisible mass to galaxies, MOND changes Newton's law itself. At very low accelerations, it makes gravity stronger than expected. The result? Galaxy rotation curves fall into place, no dark matter required. MOND is elegant in its simplicity. It introduces a single new constant, a threshold below which Newton's laws start to bend. When accelerations are above this threshold, everything behaves as expected. But below it, in the outer edges of galaxies, for instance, gravity becomes stronger. This tweak alone reproduces the flat rotation curves that launched the dark matter crisis in the first place. And it works remarkably well at the scale of individual galaxies. MOND predicts rotation speeds, velocity profiles, and even the Tully-Fisher relation between mass and luminosity. It does so with fewer assumptions than dark matter models, which often rely on simulations and fitting parameters. For galaxy dynamics, MOND is shockingly accurate. But the theory stumbles as we zoom out. MOND struggles to explain galaxy clusters. The motions of galaxies inside clusters suggest more mass than MOND can account for. Lensing observations, especially in systems like the bullet cluster, don't match the predictions. MOND can't explain the separation between visible matter and gravitational lensing centers. Dark matter handles this naturally. MOND doesn't. To address this, extensions to MOND have been proposed, like TEVS, tensor vector scalar gravity, trying to merge MOND with relativistic physics. These variants attempt to include lensing, cosmic expansion, and the microwave background. But with each layer, the elegance fades. MOND becomes more complex, more speculative, and still, some inconsistencies remain. Another issue is the cosmic microwave background. The fine-scale fluctuations observed by WIMP and Planck match predictions made by models that include dark matter. MOND has a harder time producing those patterns without invoking something like dark matter anyway, undermining its original appeal. In trying to explain everything, it circles back to the very thing it tried to avoid. Yet MOND persists because it's precise where dark matter is vague. Dark matter explains galactic behavior statistically, on average, in large samples. MOND makes direct, testable predictions for individual galaxies, and often it gets them right. This precision keeps the theory alive, especially among researchers focused on galactic dynamics. It also reveals gaps in the dark matter paradigm. If MOND can match rotation curves with no free parameters, why do dark matter models need so many tweaks? Why do they sometimes fail to predict galaxy behavior without tuning? MOND's success, even if incomplete, points to something missing in our understanding of either gravity or dark matter distribution. In this way, MOND acts as both theory and provocation. It challenges assumptions, exposes weak spots, and demands that dark matter models do better. Even if it never replaces them, it sharpens the tools used to test them. In science, even failed theories play a role. They refine the questions, force deeper rigor, and keep alternatives alive. Some researchers now pursue hybrid approaches. Maybe gravity is modified and there's some dark matter. Maybe the truth lies in between. MOND could describe galactic dynamics while dark matter explains clusters and cosmic evolution. A dual theory, messy but effective. Ultimately, MOND reminds us that elegance isn't enough. A good theory must work everywhere, not just in specific cases. MOND almost does, but almost isn't enough when the cosmos is this demanding. Still, its persistence hints at a deeper truth. Whether MOND is right or not, gravity might be trying to tell us something new. Ancient supernovae that changed how we see the cosmos. In the late 1990s, two independent teams of astronomers set out to measure how fast the universe is expanding. Their method? Observing Type Ia supernovae, stellar explosions so consistent in brightness they act as standard candles. By comparing their brightness to their redshift, scientists could calculate both distance and expansion rate. What they found shocked everyone. The universe wasn't slowing down, it was speeding up. This discovery contradicted decades of expectation. Cosmologists assumed that gravity would gradually slow the expansion over time. Some models even predicted a future collapse. But the supernova data told a different story. Distant supernovae were dimmer than expected, meaning they were farther away than they should be. That could only happen if expansion had accelerated, stretching space more than anticipated. The two teams, the Supernova Cosmology Project and the High Z Supernova Search, came to the same conclusion independently. Their data was cross-checked, models scrutinized, and errors ruled out. What remained was undeniable. Something was pushing the universe apart faster over time. It wasn't just expansion, it was accelerated expansion, and it demanded a new ingredient in the cosmological recipe. That ingredient became known as dark energy. It was not matter, not radiation, and not anything familiar. But it had to exist, or the supernova observations wouldn't make sense. Dark energy didn't just join the model of the universe, it came to dominate it. According to current estimates, it makes up about 68% of the total energy content of the cosmos. Type Ia supernovae were ideal for this discovery because of their uniform behavior. They result from white dwarfs in binary systems reaching a critical mass and detonating. Their peak brightness is nearly identical, allowing them to act as precise distance markers. By mapping hundreds of them at different redshifts, astronomers could reconstruct the expansion history of the universe and reveal its strange acceleration. The implications went beyond astronomy. This was not just a tweak to a number, it was a shift in how we understand space-time itself. The accelerating universe meant there had to be a force embedded in the vacuum of space, pushing galaxies apart with increasing strength. Einstein had once introduced a cosmological constant to keep the universe static. Now, a century later, it seemed he had been right for the wrong reason. Subsequent measurements confirmed the finding. Observations from the Sloan Digital Survey, the cosmic microwave background, and baryon acoustic oscillations all supported the existence of dark energy. It wasn't an anomaly, it was a feature. The more precisely we measured the cosmos, the clearer it became. Something repulsive and pervasive fills the fabric of space. The supernovae also changed how we think about the fate of the universe. If expansion continues to accelerate, galaxies will drift ever farther apart. Stars will die, galaxies will fade, and the cosmos will grow cold and empty. This potential future, the Big Freeze, is driven by dark energy. The supernova light, flickering from billions of years ago, pointed toward a slow, inevitable solitude. More practically, this discovery triggered a massive scientific shift. Telescopes, satellites, and entire missions were redesigned to study dark energy. The Wide Field Infrared Telescope, now the Nancy Grace Roman Space Telescope, was planned specifically to map it. Supernovae became more than explosions, they became cosmological tools. Ironically, supernovae were once feared, seen as violent, chaotic events. Now they're some of our most precise instruments. Each detonation offers a snapshot of cosmic history. Their light travels for billions of years, crossing expanding space, carrying the message of a universe in motion. That message? We're accelerating into the unknown. This revelation also added urgency to the search for new physics. The standard model of particle physics doesn't explain dark energy, nor does general relativity without fine-tuning. It's a sign that something fundamental is missing. And it all began with the soft light of ancient explosions, flickers in the dark, that changed everything. Type Ia supernovae showed us that the cosmos isn't coasting, it's racing. And what began as a simple measurement of distance became one of the most important discoveries in modern science. Dark energy, the force making the universe race faster. Dark energy is one of the most mysterious concepts in modern physics, not because we know too little, but because we only know what it does, not what it is. It acts as a repulsive force, pushing the universe apart at an ever-increasing rate. It doesn't cluster like matter. It doesn't shine. It simply stretches space itself, silently reshaping the cosmos. And it's everywhere. Its discovery came from the study of Type 1a supernovae, which revealed that the universe's expansion is accelerating. This was unexpected. Gravity should have been slowing everything down. Instead, something was counteracting it, not just balancing it, but overpowering it. That something was dubbed dark energy, a term as vague as the mystery it represents. The simplest explanation for dark energy is the cosmological constant, denoted by the Greek letter lambda. It's a constant energy density that fills space uniformly, even in a perfect vacuum. Einstein first introduced it to balance the universe, then rejected it after Hubble showed the universe was expanding. But in light of dark energy, lambda came back, this time not to keep space static, but to make it accelerate. Mathematically, the cosmological constant works. It fits the observations. But physically, it's troubling. Quantum field theory predicts vacuum energy, but the predicted value is 10 to the 120th times larger than what we observe. That's the worst mismatch between theory and experiment in all of science. Why is the vacuum energy so small, yet not zero? No one knows. This mismatch has led scientists to explore alternatives. Some propose that dark energy isn't constant, but dynamic, evolving over time. These models, grouped under the name quintessence, imagine a new scalar field permeating space. It changes slowly, affecting expansion differently in the past and future. This idea opens rich possibilities, but adds new uncertainties. Other theories suggest dark energy is a sign that general relativity breaks down on cosmic scales. Maybe gravity itself changes over time. Maybe extra dimensions affect how space stretches. These ideas are harder to test, but they highlight how deep the mystery runs. Dark energy touches the very laws that shape the universe. Despite the name, dark energy isn't energy in any traditional sense. It doesn't fuel reactions or heat objects. It's more like a property of space, a built-in tendency to expand. As space grows, so does dark energy. Unlike matter, which thins out as it spreads, dark energy's density stays constant. That means the more the universe expands, the stronger dark energy's influence becomes. This leads to strange consequences. In the far future, dark energy could dominate completely, tearing apart galaxy clusters, then galaxies, then stars. Some models even predict a big rip, where expansion becomes infinite in finite time. Others suggest a steady drift into emptiness. Either way, dark energy sets the pace of the universe's endgame. To understand it better, scientists are building instruments to map cosmic acceleration. Projects like the Euclid Telescope, the Roman Space Telescope, and the Dark Energy Survey aim to chart millions of galaxies, measuring how structures grow over time. If dark energy changes, these surveys might detect it. If it's truly constant, we'll at least know its limits. For now, the data supports a simple picture. About 68% of the universe is dark energy, 27% is dark matter, and only 5% is the normal matter we know. This means everything we've ever touched, seen, or measured is a cosmic minority. Dark energy isn't a footnote, it's the main chapter, and it's written in a language we still can't translate. The deeper we study dark energy, the more it resembles a blank space in our equations, a placeholder for something profound. It behaves like a constant, but resists explanation. It governs the universe's future, yet leaves no signature we can isolate. It's both subtle and dominant, a force we can't escape, but can barely define. Dark energy is not an object, a field, or a wave. It's a shift in the universe's behavior, a curve in the graph that defies expectation. And although we can't bottle it, see it, or measure it directly, its fingerprints are everywhere. Every time space expands a little faster, it's dark energy pulling the strings. Einstein's greatest mistake that turned out to be right. In 1917, Albert Einstein added a term to his equations of general relativity. It was called the cosmological constant, represented by the Greek letter lambda. At the time, he believed the universe was static, neither expanding nor contracting. But gravity, according to his own theory, should cause the universe to collapse. So he inserted lambda to counterbalance gravity and keep space stable. Years later, Edwin Hubble discovered that the universe was expanding. Einstein realized that his assumption of a static universe was wrong, and with it, the need for the cosmological constant. He reportedly called it his greatest blunder. He had added a term to fix a problem that didn't exist. But in a twist of irony, that very term would return decades later and reshape modern cosmology. In the 1990s, supernova data revealed that the universe's expansion wasn't just continuing, it was accelerating. The only way to explain this was to reintroduce a repulsive term into Einstein's equations, and the simplest candidate was the same lambda he had once discarded. Suddenly, Einstein's mistake became the foundation of the dark energy model. Today, lambda is central to the standard model of cosmology, the lambda CDM model. It accounts for the acceleration of the universe's expansion and aligns with observations of supernovae, the cosmic microwave background, and large-scale structure. In a sense, Einstein predicted dark energy before anyone even knew it existed, not by intention, but by mathematical necessity. But what exactly is lambda? That's the mystery. It behaves like a constant energy density embedded in empty space, a pressure that doesn't weaken as the universe grows. This defies intuition. Most forms of energy dilute with expansion, but lambda stays constant, meaning its total influence increases over time. More space means more dark energy. Quantum physics offers a possible connection. The vacuum, according to quantum field theory, is never truly empty. It's filled with fluctuating virtual particles and fields. These should contribute a background energy, vacuum energy. But the calculated value is catastrophically large, 120 orders of magnitude greater than what we observe. That's the biggest mismatch in all of science. This absurd discrepancy has puzzled physicists for decades. Why is the observed cosmological constant so small, yet not zero? What cancels out those quantum contributions so perfectly, but leaves just enough to drive cosmic acceleration? No one knows. It's like tuning a radio to near silence, but still hearing a whisper that reshapes the universe. Some researchers believe lambda is truly fundamental, a new constant of nature we must accept. Others think it hides deeper structure, such as dynamic fields or interactions we haven't yet discovered. Still others propose multiverse explanations, where our universe happens to have a lambda compatible with life, and countless others do not. Regardless of interpretation, lambda now guides our understanding of cosmic fate. If it remains constant, the universe will expand forever, becoming colder and emptier. If it grows stronger, more exotic endings like the Big Rip could occur. If it decays, the acceleration might slow or even reverse. Lambda isn't just a number, it's the key to the universe's future. Einstein never saw the revival of his discarded idea, but his equations, built on geometric elegance, were resilient enough to adapt. They didn't need rewriting, just reinterpreting. The cosmological constant was never truly a blunder. It was a puzzle piece without a picture. Now the picture is coming into view, and lambda sits at the center. This turn of events is a rare moment in science. A theoretical patch, once rejected, becomes essential decades later. It reminds us that ideas in physics are rarely dead, only waiting for the right data. Einstein's greatest mistake might also be his most lasting legacy, not because it was wrong, but because it became right again. And so the term he once erased now defines how we model the universe. The cosmological constant, a quiet placeholder in an old equation, became the force shaping everything. The universe looks flat, but something strange holds it that way. One of the strangest things we've learned about the universe is that it appears geometrically flat. That means, on the largest scales, space isn't curved inward like a sphere or outward like a saddle. It's flat, like a giant three-dimensional plane. This flatness has been confirmed through multiple observations, including precise measurements of the cosmic microwave background. But here's the mystery. Flatness is unstable. In theory, any small deviation from perfect flatness in the early universe should have grown over time. A tiny bit of positive curvature would have become dominant. A slight negative curvature would have expanded wildly. Maintaining a flat universe over billions of years requires extremely fine-tuned conditions in the beginning, or something that constantly balances the geometry. This problem is known as the flatness problem, and it puzzled cosmologists for decades. The question was, why does the universe appear flat now unless it was perfectly tuned at the start? The odds of this happening by chance are astronomically low. But the data is clear. The universe today is flat, to within a tiny margin of error. One proposed solution came from inflation theory, the idea that the universe underwent a rapid exponential expansion in its first fraction of a second. This inflation would have stretched any initial curvature, making the universe look flat regardless of its original shape. It's like zooming in on a tiny patch of a balloon. The more it expands, the flatter it appears locally. But dark energy complicates the picture. As the universe expands faster and faster, driven by this mysterious repulsive force, the geometry remains flat. That shouldn't be guaranteed, yet flatness persists as if something continues to enforce it. Some theorists suggest that dark energy acts as a geometric stabilizer, not just stretching space, but preserving its shape. The cosmic microwave background offers some of the strongest evidence. The size of fluctuations in the CMB depends on the geometry of space. In a curved universe, hot and cold spots would appear distorted, but in our universe, they appear just as expected for flat geometry. The Planck satellite confirmed this with astonishing precision. However, not everyone agrees that flatness is fully explained. Inflation can smooth curvature, but it doesn't predict why the post-inflation universe should stay flat indefinitely. And dark energy, as currently modeled, doesn't care about geometry. It simply expands space. So why doesn't curvature creep back in over billions of years? Some alternative theories propose that flatness arises from deeper symmetries in the laws of physics, symmetries we haven't yet discovered. Others suggest that what we perceive as flatness may be an illusion, based on limited data or assumptions about cosmic homogeneity. But no model has yet replaced the standard view. Adding to the mystery is the fact that a flat universe is just on the edge between eternal expansion and eventual collapse. It represents a delicate balance, the critical density where everything could go either way. And somehow, our universe sits right on that edge. Coincidence? Or is something enforcing this balance? This question connects to the broader mystery of cosmic fine-tuning, the idea that many of the universe's properties seem precisely calibrated for long-term structure and evolution. Flatness is one of the sharpest examples. It's not just geometry. It's a clue that the universe evolved under constraints we don't fully understand. For now, the flatness of the universe remains one of cosmology's most elegant puzzles. It matches observations, fits our models, and yet hints at something deeper. Geometry, once thought to be a passive background, might be an active player in the cosmic story. And while the universe may appear flat, the mystery behind that flatness is anything but simple.
Does the vacuum have energy? The answer could rewrite modern physics. Empty space isn't truly empty. According to quantum field theory, what we call vacuum is a seething foam of invisible activity. Virtual particles constantly appear and disappear, borrowing energy from the uncertainty principle. This ever-present background isn't just mathematical, it should have real, physical consequences. And one of them might be the most mysterious force in the universe, dark energy. In quantum theory, every field, electromagnetic, gravitational, Higgs, has a lowest possible energy level, even when no particles are present. This baseline energy, called vacuum energy, is predicted to permeate all of space. It doesn't come from atoms, radiation, or any matter at all. It's the energy of nothing, and it might be what's causing the universe to accelerate. This idea became important after the discovery of the universe's accelerating expansion. Dark energy behaves exactly like a vacuum energy, constant, uniform, and non-diluting. The more space exists, the more total dark energy there is. It fits the behavior of a cosmological constant, a pressure built into space-time itself. But the problem isn't the concept, it's the number. When physicists calculate vacuum energy using known quantum fields, the result is enormous, about 10 to the 120th times larger than what dark energy actually seems to be. This is the biggest known mismatch between theory and observation in all of physics. The vacuum should have torn the universe apart long ago. But it didn't. Instead, it's gently accelerating space. That gap remains unexplained.
Some suggest unknown symmetries cancel out most of the vacuum energy, leaving only a tiny residue, just enough to act as dark energy. Others invoke the anthropic principle. If the vacuum energy were much larger, galaxies wouldn't form, and observers like us wouldn't exist. So we observe a small value because it's the only kind of universe we could live in. It's not satisfying, but it's logically consistent. Still, the idea that empty space contains measurable energy has experimental support. The Casimir effect, for instance, shows that two metal plates in a vacuum attract each other slightly due to changes in vacuum energy between them. This doesn't prove dark energy exists, but it confirms that the vacuum isn't truly empty. It has structure, and that structure has consequences. Some cosmologists believe dark energy could be a false vacuum, a temporary state that might someday decay into a true vacuum. If that happened, the universe would undergo a phase transition, like water freezing into ice. Except in this case, the change would rewrite the laws of physics themselves. It's a hypothetical, but the math checks out, and it's unsettling. The concept of vacuum energy also influences inflation theory. In the early universe, a high-energy vacuum state drove exponential expansion, smoothing out the cosmos. That inflationary vacuum eventually decayed, releasing energy that became matter and radiation. If dark energy is a similar mechanism, it may be a distant echo of the universe's birth. But even with these connections, no one has directly measured vacuum energy in the cosmological sense. We infer its presence from the universe's acceleration, but we don't know what's truly behind it. It could be vacuum energy, a dynamic field, or something entirely new. We're measuring shadows cast by a force we can't yet describe. This mystery also intersects with quantum gravity. If space has energy, how does that energy bend space-time? How does it interact with general relativity? No unified theory exists. String theory offers some ideas, as do loop quantum gravity models, but none are complete. Dark energy may be the key to merging quantum physics with gravity, the holy grail of modern science. And so, the vacuum, once thought to be nothing, may be everything. It holds energy, it shapes space, it drives the expansion of the universe, and it refuses to fit our equations. Understanding it means rethinking the nature of space itself, not as a backdrop, but as an active participant in the cosmos. The idea that nothing has power sounds absurd, but in physics, the vacuum may be the most energetic, most dominant, and most mysterious component of all. And the more we stare into empty space, the more we realize it's not empty at all. Does anti-gravity exist? Yes, but not the way you think. When people hear anti-gravity, they often imagine science fiction, floating cars, force fields, or levitation devices. But in physics, anti-gravity refers to something very real and far stranger. It's not about reversing gravity, it's about creating a repulsive force that pushes matter apart. And this is exactly what dark energy appears to do. Not fantasy, just misunderstood. In Einstein's equations of general relativity, energy and pressure both curve spacetime. Normally, matter and radiation produce attractive curvature. That's what we experience as gravity. But if a substance has negative pressure, it curves spacetime in the opposite way. It causes repulsive gravity. That's not speculation. It's a direct consequence of Einstein's math. Dark energy, modeled as a cosmological constant, fits this description perfectly. It has constant density and negative pressure. That pressure causes space to expand faster and faster, pushing galaxies apart. It's not pulling them in, it's pushing them away. This is the most literal form of anti-gravity in known physics. Expansion driven not by momentum, but by the properties of space itself. This repulsive gravity doesn't cancel normal gravity locally. On small scales, like planets, stars, or even galaxies, dark energy is negligible. Gravity still dominates. But on cosmic scales, where space stretches over billions of light years, dark energy becomes stronger. The bigger the space, the more it expands. It's anti-gravity with a scale-dependent effect. This also explains why we didn't notice it earlier. In the early universe, matter was dense and gravity dominated. Only when the universe expanded and matter thinned out did dark energy take over. That tipping point occurred a few billion years ago, and now acceleration continues to grow. Anti-gravity didn't suddenly appear. It was always there, just hidden beneath gravity's weight. Interestingly, anti-gravity isn't limited to cosmological models. Some speculative physics, like scalar field theories, allow for temporary anti-gravitational effects in high-energy environments, but these are highly theoretical and unconfirmed. The only anti-gravity we've actually observed is dark energy's large-scale effect on space-time, and that's enough to change everything. This kind of anti-gravity also raises deep questions. What happens if it increases over time? Will it tear galaxies apart? Will it stretch atoms? This leads to the Big Rip scenario, where acceleration becomes so extreme that all structure in the universe is destroyed. It's speculative, but mathematically consistent with current models. The fact that energy can curve space in two directions, attractive or repulsive, is a fundamental feature of general relativity. It shows that gravity isn't a one-way street. It depends on the form of energy involved. Positive energy with normal pressure pulls. Constant energy with negative pressure pushes. That's the duality at the heart of cosmic dynamics. This makes dark energy more than a curiosity. It's a test case for extreme physics, one that operates on the biggest scales but comes from subtle properties. Its behavior forces physicists to rethink assumptions about space, time, and energy. It's not a patch to the theory, it's a revelation that the theory contains more than we realized. And yet we don't know what dark energy is, we only know what it does. It accelerates expansion. That action, by definition, is anti-gravity. Not magic, not myth, just a force we can't feel directly, but which dominates the fate of the cosmos. So yes, anti-gravity exists, not in flying machines, but in the fabric of space itself. It doesn't defy physics, it emerges from it. And every second, across billions of light years, it's pushing the universe a little farther apart. What if dark energy is alive and changing? The simplest model of dark energy is a constant, a fixed energy density that fills all of space and never changes. But what if that simplicity is misleading? What if dark energy isn't constant, but dynamic, slowly evolving over time? That's the idea behind quintessence, a class of theories that treat dark energy as a field, not a number. It doesn't just exist, it changes. Quintessence introduces a new scalar field to the universe, something like the Higgs field but cosmological in scale. This field would vary in time and space, creating a form of energy that drives expansion differently depending on its state. Unlike the cosmological constant, quintessence can speed up or slow down over time. It's not a static pressure, it's a moving force. In this model, the behavior of dark energy depends on the shape of its potential energy curve. Some versions accelerate the universe more in the past, others predict future deceleration. Some even allow for oscillations or tracking behavior, where the field adapts to the energy content of the universe. This flexibility makes quintessence harder to pin down, but potentially more accurate. One of the biggest motivations for quintessence is the fine-tuning problem. The cosmological constant requires its value to be unimaginably small and precise, but a dynamic field might relax into this value naturally, avoiding awkward coincidences. It could evolve into the observed energy density rather than starting with it. That would solve one of dark energy's most persistent puzzles. Another advantage is testability. Unlike a constant, a changing field leaves imprints. It affects the rate of expansion differently at different epochs. By measuring the growth of cosmic structure, the distribution of galaxies, and the behavior of gravitational lensing, astronomers can look for signs of time variation. Quintessence makes predictions, and that makes it vulnerable to data. But so far, observations show no obvious deviation from a constant. The best fits still support a cosmological constant, at least within current measurement precision. If quintessence exists, it must be evolving very slowly. That doesn't rule it out, but it narrows the range of possible models. It also raises the question, is complexity necessary, or is nature just simple? Some versions of quintessence include phantom energy, where the equation of state drops below -1. This leads to bizarre futures like the Big Rip, where dark energy grows so powerful it tears apart galaxies, stars, and atoms. Other models predict a future phase transition where dark energy could switch off, slow down, or even reverse. In this sense, quintessence introduces not just flexibility, but danger. There are also hybrid models. Some suggest dark energy began as quintessence and settled into a cosmological constant later. Others propose that the field interacts with dark matter, creating feedback loops or complex behaviors. These ideas move toward a unified dark sector, where multiple invisible components influence each other in ways we haven't yet detected. Despite its appeal, quintessence faces theoretical challenges. It must be extremely light and long-range, yet stable and minimally interactive. Building such a field within the framework of quantum field theory is non-trivial. It risks introducing instabilities or unexplained tuning unless extra symmetries are added, making the theory more elaborate. Still, the quest for quintessence continues. Future missions like the Roman Space Telescope and Euclid aim to detect tiny changes in cosmic acceleration. If they find that dark energy's influence has changed over time, it would be a blow to the cosmological constant and a huge win for quintessence. A dynamic universe may be hiding behind our static assumptions. In that case, dark energy wouldn't just be a passive backdrop. It would be a living part of the cosmos, slowly evolving, shaping the universe's destiny. And understanding it would require more than measuring a number. It would demand tracking a force in motion. Quintessence offers a possibility that the universe isn't governed by constants, but by change. Subtle, powerful, and everywhere. What if dark energy is a trick of time itself? Dark energy looks like a force, something that pushes the universe apart. But some physicists have suggested a very different possibility. What if dark energy isn't a force at all? What if it's a misinterpretation of time, a side effect of how we measure cosmic expansion, not a substance in the universe? This radical idea questions one of our deepest assumptions, that time flows uniformly everywhere. In standard cosmology, time is treated as a global clock. All observers agree on the rate of expansion, and the passage of time is baked into the equations. But what if this isn't quite true? What if the flow of time is not the same in all regions or changes depending on the curvature of space? Then the apparent acceleration might be an illusion caused by averaging clocks that tick at different rates. This concept appears in models that challenge the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. These models suggest that the universe may contain large-scale structures, voids, or inhomogeneities that distort our measurements of time and distance. When we observe redshift, we might be misreading the expansion due to complex time effects. One such idea is the timescape cosmology, proposed by David Wiltshire. In this model, observers inside dense regions, like galaxies, experience time differently than those in vast cosmic voids. When we average over all these regions, we interpret the result as accelerated expansion, even if no dark energy exists. It's a subtle, geometry-based rethinking of cosmic time. Another approach involves emergent time, where time is not fundamental, but arises from deeper quantum variables. In this view, dark energy could be a side effect of how time emerges in an expanding universe. The acceleration isn't driven by a force, it's a manifestation of time's structure itself. It sounds exotic, but some quantum gravity theories predict similar effects. If true, this would mean that our equations describe the universe correctly, but we're mislabeling the source of acceleration. There's no mysterious energy in the vacuum. Instead, the geometry of space-time and the way time flows within it causes the observed expansion pattern. It's not that space is accelerating, it's that we're reading the clock wrong. Testing these ideas is difficult. They often make predictions similar to dark energy models, especially when adjusted for known data. But small differences can appear in how galaxies cluster, how gravitational lensing behaves, or how the universe looks in the distant past. Upcoming missions may help distinguish between true acceleration and time-based illusions. One challenge is explaining the observed uniformity of the cosmic microwave background. If time flows differently in different regions, why is the early universe so smooth? Proponents argue that initial conditions or early inflation could have evened out the wrinkles, but it remains a debated point. Simpler models still have the edge in parsimony. Another challenge is philosophical. If time itself is variable, what does that say about cause and effect, entropy, or the arrow of time? While these questions are beyond the scope of cosmology, they highlight the radical nature of this hypothesis. Dark energy, in this view, becomes not a mystery to be solved, but a clue that our concept of time is incomplete. Still, the idea has one great strength. It avoids inventing new particles or fields. Instead of adding to the universe's content, it reinterprets what we already observe. It's a shift in perspective, not a shift in physics. And sometimes, that's all it takes to see a problem in a new light. If time can vary, then acceleration might be a mirage, a projection caused by the way space-time organizes itself. Not less real, just less obvious. A trick, not of the universe, but of our assumptions. In that case, dark energy wouldn't be a substance at all. It would be the echo of time, folded into the equations and waiting to be redefined.
Dark matter and dark energy, two different shadows. They sound similar, dark matter and dark energy. Both are invisible, both dominate the cosmos, and both defy our instruments. But despite the shared adjective, they are completely different. One pulls, the other pushes. One clusters, the other spreads. Understanding their differences is essential to avoid a common misconception that they're two faces of the same thing. Dark matter acts like invisible mass. It doesn't emit or absorb light, but it exerts gravity, binding galaxies and clusters together. It behaves like a fluid of particles moving through space and forming halos around galaxies. Its presence is inferred from the rotation of galaxies, gravitational lensing, and cosmic structure formation. It pulls things in. It doesn't push them apart. Dark energy, on the other hand, is diffuse and repulsive. It doesn't clump, doesn't form structures, and doesn't behave like matter at all. It seems to fill space uniformly, exerting negative pressure that causes the universe to expand faster over time. While dark matter explains why things stay together, dark energy explains why space itself accelerates. They also dominate at different scales. Dark matter governs the dynamics of galaxies, clusters, and the cosmic web. Its influence is local and structural. Dark energy, in contrast, dominates the cosmic scale, shaping the overall expansion of the universe. It's smooth, omnipresent, and only reveals itself when looking at billions of light-years. Their theoretical treatments differ too. Dark matter is often modeled as a particle, something that might be detected in experiments. Candidates include WIMPs, Axions, or sterile neutrinos. Dark energy, however, might not be a particle at all. It could be a property of space, a field, or a modification of gravity. Its nature is more abstract, more elusive. Even their timelines are different. Dark matter influenced the universe early on, helping form the first galaxies. Its effects show up in the cosmic microwave background.
Dark energy, by contrast, became dominant much later, only when the universe expanded enough for its repulsive force to overcome gravity. One shaped the beginning, the other controls the future. Despite these contrasts, both are essential to the standard model of cosmology. Together, they account for 95% of the universe's total energy budget. Baryonic matter, everything we see and touch, makes up only 5%. This means our entire understanding of the cosmos rests on things we can't directly observe. We're modeling shadows, not sources. There have been attempts to unify them. Some theories propose that dark matter and dark energy are manifestations of a single field. Others suggest they interact in subtle ways, perhaps exchanging energy or influencing each other's behavior. These dark sector models are speculative, but they aim to reduce the number of unknowns by finding hidden connections. Still, no experiment has confirmed such a link. Dark matter behaves like mass. Dark energy behaves like vacuum energy. Their roles, dynamics, and signatures are distinct. Lumping them together risks confusion. In science, naming matters, and so does clarity. They are both dark, but they are not the same. Understanding one won't automatically explain the other. Each has its own puzzles, its own search strategies, and its own implications. Conflating them oversimplifies the challenge. To solve the dark universe, we must treat each component on its own terms and resist the temptation to assume symmetry where there may be none. So the next time you hear dark matter or dark energy, remember, they're not partners in mystery. They're separate shadows cast by very different sources. We live in a universe where 95% is a complete mystery. Imagine a book where only 5% of the pages are written and the rest are blank. That's how much we currently understand about the universe. Ordinary matter, atoms, stars, gas, and galaxies, makes up just 5% of the cosmic total. The remaining 95% is composed of dark matter and dark energy, whose nature remains unknown. We're surrounded by the invisible. This realization is one of the most profound in modern science. For centuries, we thought we understood the cosmos by studying light. Telescopes, spectrometers, and satellites gave us detailed maps of stars and galaxies, but all of that is built from baryonic matter, the familiar particles of protons, neutrons, and electrons. The rest doesn't shine, and yet it dominates. Dark matter makes up about 27% of the universe. It doesn't emit light, but it exerts gravitational force. Without it, galaxies wouldn't form or rotate as they do. It acts as scaffolding for cosmic structure. Dark energy is even more mysterious, accounting for about 68% of the universe. It seems to fill space and push it apart. Together, they outnumber us 19-1. The standard model of cosmology, known as LCDM, accommodates these components, but it doesn't explain them. It's a framework, not a full theory. We can model what dark energy and dark matter do, but we can't yet say what they are. That's like mapping the wind without knowing air exists. This imbalance raises a philosophical question. How can science be so successful when it knows so little? The answer lies in indirect evidence. Gravity, light bending, cosmic background radiation, all of these carry the fingerprints of the unseen. It's not guesswork, it's measurement of absence, inference of presence. Still, the fact remains, most of the universe is hidden. We're not missing a detail, we're missing almost everything. That means our current theories are not final answers. They're placeholders, waiting to be replaced or expanded by deeper understanding. Like Newtonian gravity before Einstein, they work, but they're not complete. This ignorance also shapes research priorities. Entire fields now focus on detecting dark matter, measuring dark energy, or redefining the laws of gravity. Telescopes like Euclid, Vera, Rubin, and the Roman Space Telescope are designed not to look at stars, but to look for the invisible. The goal is not to admire the cosmos, it's to decipher it. Some physicists argue that this 95% mystery is a sign we've hit a wall, that we need a new paradigm, maybe even a new kind of physics. Others see it as a normal part of scientific progress. Each breakthrough reveals new gaps. Either way, it's a humbling moment. We are cosmic cartographers mapping with incomplete tools. This 5% window is also where life exists. Stars, planets, biology all emerge from the sliver of matter we understand. That makes our perspective both privileged and limited. We are made of the rare stuff, living in a universe dominated by things we cannot touch. We study the cosmos from within a bubble of matter surrounded by shadows. Yet this doesn't make science weaker. It makes it more urgent. Because if we've come this far with 5%, imagine what we'll discover when we begin to unlock the other 95%. The biggest discoveries may not be behind us, but ahead, in the unknown. We live in a mysterious universe, and that's not a poetic metaphor. It's a numerical fact.
Dark matter, why 85% of the universe is hidden from us. When astronomers observe galaxies, they find something strange. The stars at the edges move much faster than they should, based on visible mass. According to Newtonian physics, they should drift away, but they don't. Something holds them together, something invisible yet massive. This is how we discovered dark matter. Dark matter makes up about 85% of all matter in the universe. It doesn't emit or absorb light, which is why telescopes can't see it. But it exerts gravitational force, shaping the rotation of galaxies and the behavior of clusters. Its presence is measured not by detection, but by its effects. It's everywhere, except in our instruments. In spiral galaxies, rotation curves flatten out rather than fall off. This suggests that most mass lies outside the visible disk, forming an extended halo. The same applies to galaxy clusters, where galaxies move faster than expected. Without extra mass, they should fly apart. Dark matter binds them, not metaphorically, but literally. Gravitational lensing also confirms dark matter. When light from distant galaxies passes near massive objects, it bends. In many cases, the lensing effect is stronger than what visible matter alone could produce. This extra gravity maps the dark matter distribution, revealing structures that light can't show. It's like sketching a shadow from its distortions. The cosmic microwave background offers more evidence. Tiny fluctuations in the early universe's radiation match models that include dark matter. Without it, the density patterns wouldn't evolve into the galaxies we see today. Simulations with dark matter match observations almost perfectly. Without it, the structure of the cosmos collapses. But what is dark matter? That's the puzzle. It must be non-baryonic, meaning it's not made of protons and neutrons. It interacts weakly, if at all, with electromagnetic force. This rules out regular atoms, dust, or gas. Leading candidates include WIMPs, Axions, or other exotic particles that rarely interact with normal matter. If dark matter were made of massive particles, we should detect them with direct detection experiments, deep underground labs shielded from noise. So far, they've seen nothing. Indirect searches, looking for signals from dark matter annihilation, also remain inconclusive. It's as if the particles are there, but never leave a trace. Alternative theories exist. Some physicists propose modified gravity, like MOND, to explain galactic motion without dark matter. But these models struggle at larger scales, like galaxy clusters or lensing patterns.
Most evidence still favors a real, invisible substance, even if we don't yet know its identity. Dark matter doesn't just explain motion, it sculpts the universe. It seeded the formation of galaxies by amplifying early density fluctuations. Ordinary matter then followed, collecting in the gravitational wells formed by dark matter halos. We owe our existence, in part, to this hidden scaffold. The fact that 85% of matter is invisible highlights a gap in our understanding. We've mapped its influence, measured its weight, and modeled its effects, yet we still don't know what it is. That means we understand only a fraction of the cosmos. The rest remains cloaked in gravity, waiting to be revealed. Dark matter is real, not because we see it, but because the universe doesn't make sense without it.
Dark energy. What decides whether the universe freezes to death? As the universe expands, galaxies move farther apart. But this expansion isn't just continuing, it's accelerating. Something is pushing space itself to grow faster over time. That mysterious force is called dark energy, and it now dominates the universe's energy balance. It's not just shaping the cosmos today, it may decide how the universe will end. Current observations suggest that dark energy accounts for about 68% of the universe's energy content. Unlike matter or radiation, it doesn't dilute as space expands. It remains constant, or nearly so, as the universe grows. That means its influence increases over time. Gravity weakens, expansion wins. If dark energy remains constant forever, the universe will face a heat death. Galaxies will recede beyond each other's horizons, stars will burn out, black holes will evaporate. Eventually, all matter will be isolated and cold. No new structure will form. This scenario is called the Big Freeze, and it's currently the most supported outcome. But that future depends on the exact behavior of dark energy. If it changes over time, the fate of the universe could shift. Some models suggest that dark energy could increase, leading to a big rip, where galaxies, stars, planets, and even atoms are torn apart by runaway expansion. It's extreme, but mathematically possible. Other theories propose the opposite. Dark energy might decay. If it diminishes or turns negative, the expansion could slow, halt, or even reverse. This would lead to a big crunch, where the universe collapses back into a dense state. This model has lost favor, but it's not ruled out. It all depends on how dark energy behaves. Cosmologists study this behavior through the equation of state, denoted as W. If W equals -1, dark energy behaves like a cosmological constant. If W varies over time, it suggests a dynamic field like quintessence. Precise measurements of W and how it changes are key to predicting the universe's fate. Telescopes like Euclid and the Roman Space Telescope aim to track this evolution by measuring how galaxies spread over time. They look for patterns in expansion history and structure formation. These data constrain models of dark energy and help forecast the distant future. We're building a timeline not just of the past, but of what's to come. Even small changes in W could radically alter the endgame. If it drops below -1, expansion accelerates violently. If it climbs above -1, expansion could stabilize. We're talking about differences in the third decimal place, but they determine whether the universe ends quietly or catastrophically. This makes dark energy not just a theoretical curiosity, but a cosmic decision-maker. It holds the balance between eternal expansion, collapse, or destruction. And yet, we don't know what it is.
We're observing its consequences, but not its cause. If we ever identify the true nature of dark energy, whether as a field, a fluid, or something else, we may finally predict the universe's destiny with confidence. Until then, we live under the rule of an unknown force, guiding the expansion of everything. The end of the universe may already be written in the behavior of dark energy. The Big Rip, the scenario where everything, even atoms, gets torn apart. What if the expansion of the universe doesn't just continue, but accelerates without limit? That's the idea behind the Big Rip, a theoretical scenario where dark energy grows stronger over time. Not just enough to push galaxies apart, but enough to eventually tear apart everything, down to the atomic level. This outcome depends on the behavior of dark energy's equation of state. If the parameter W falls below -1, dark energy becomes phantom energy. In this regime, its density increases as the universe expands. That's unusual. Most things dilute. But phantom energy gets denser, pushing harder and harder as space grows. In this model, expansion starts slow, then escalates. First, galaxies drift apart beyond each other's horizons. Then, the gravitational pull holding galaxies together weakens. Stars drift from galaxies. Planetary orbits unravel. Moons fall away. Gravity loses its grip everywhere. As the process continues, even stars become vulnerable. Their cores stretch. Electromagnetic bonds weaken. Eventually, solar systems break apart. The time between each stage shrinks. The universe enters its final acceleration, a countdown to structural failure. Near the end, the expansion reaches molecular scales. Bonds between atoms can no longer resist the growing pressure. Molecules dissociate. Then atoms themselves are torn apart. Electrons and nuclei separate. Even the strong nuclear force is overcome. The universe becomes a soup of isolated particles. At the very end, even space itself is shredded. Fundamental fields like the electromagnetic field could unravel. The timeline varies by model, but in one version, galaxies unbind 60 million years before the end. Solar systems dissolve months before, and atoms rip apart in the final 10 to the -19 seconds. So far, this is purely hypothetical. Observation suggests W is close to -1, consistent with a cosmological constant. But current data can't rule out W less than -1. That means phantom energy remains possible, and so does the Big Rip. It's not the most likely scenario, but it's one of the most extreme. The Big Rip doesn't require exotic physics, just a small shift in one number. It would rewrite the fate of the cosmos, replacing heat death or the Big Freeze with a catastrophic unmaking. Unlike a sudden event, it unfolds gradually. The universe accelerates toward its own disassembly. No new particles are needed, no collapse or bounce, just relentless expansion under an unstable form of dark energy. That makes it a clean model, but a grim one. It ends with nothing bound, nothing stable, nothing intact. Future surveys will refine W's value and its variation over time. If they ever find W is less than -1, the Big Rip will move from speculative to probable. Then the clock starts ticking, not just for galaxies, but for everything. If phantom energy is real, the universe may end not with a bang, but with a rip. Simulations show, without dark matter, nothing forms. To understand the universe, astronomers build virtual models, simulations that follow the laws of physics across billions of years. One striking result emerges again and again. Without dark matter, structure doesn't form. Galaxies, stars, and even clusters fail to emerge. The universe stays smooth, featureless. This discovery comes from comparing two kinds of simulations. In one, dark matter is included, acting as gravitational scaffolding. In the other, only ordinary matter is used. The difference is dramatic. With dark matter, the cosmic web emerges, filaments, halos, galaxies. Without it, the universe remains a diffuse fog. Dark matter seeds structure early. In the infant universe, tiny quantum fluctuations were stretched by inflation. Dark matter responded first, collapsing into dense regions under gravity. Ordinary matter followed later, cooling and settling into the wells created by dark matter halos. Without these halos, gas can't collapse efficiently. This process has been modeled in thousands of simulations, from basic Newtonian codes to full relativistic models. Every time, the results agree: dark matter is essential for structure formation. It gathers mass fast, before radiation pressure can stop collapse. It drives the early stages that shape everything else. One famous simulation is the Millennium simulation, which used over 10 billion particles to map cosmic evolution. Its success in reproducing observed structures depends entirely on dark matter. The filamentary web it produces matches real large-scale surveys. No other substance creates the same pattern. Even the cosmic microwave background supports this. Its power spectrum, the detailed pattern of temperature fluctuations, matches predictions only if dark matter is included. Without it, the fluctuations are too weak, too smooth, and don't evolve into galaxies. Dark matter provides the missing gravitational kick. Some theories tried to replace dark matter with modified gravity, but these alternatives struggle in simulations. They fail to match observed galaxy clustering or the timing of cosmic reionization. They can tweak dynamics at certain scales, but not reproduce the full richness of structure we observe. Simulations also test the properties of dark matter. By adjusting its mass, speed, or interaction strength, physicists can see what kinds of structures emerge. Cold dark matter, slow-moving particles, best matches reality. Warm or hot dark matter leads to fuzzier, smaller structures, inconsistent with what we see. These experiments guide telescope design. Observing specific patterns in galaxy clustering or voids helps narrow the range of dark matter models. It's a feedback loop. Data informs simulations. Simulations guide new data. And every loop confirms the same truth: dark matter builds the universe. Without dark matter, stars don't gather, galaxies don't swirl, the cosmic web never forms, the sky stays dark. Dark matter doesn't just shape space, it makes structure possible. What the James Webb Space Telescope can see that no one else could. The James Webb Space Telescope was built to do something no other instrument could: see the earliest light in the universe. It's optimized for infrared, which allows it to look further back in time than any telescope before. Why infrared? Because the expansion of the universe stretches visible light into longer wavelengths, and JWST was designed to catch those ancient signals. By peering into deep space, JWST looks at galaxies that formed just hundreds of millions of years after the Big Bang. These are the first structures, the first stars, the first black holes, the first clusters. Their light has traveled for over 13 billion years. No previous telescope had the sensitivity or wavelength coverage to see them clearly. JWST's instruments can detect the faint glow of stars forming inside dense gas clouds. In visible light, these regions are opaque, but in infrared, the light passes through, revealing the engines of galaxy formation. That's why JWST can image the birthplaces of stars across space and time. What it finds challenges expectations. Some galaxies appear more massive and evolved than models predict for their age. Structures that shouldn't exist so early are present. The timeline of cosmic evolution may need revision. JWST isn't just seeing old light, it's exposing possible gaps in our theory. It also studies exoplanet atmospheres. By analyzing starlight filtered through distant worlds, JWST detects molecular fingerprints: water, methane, carbon dioxide. This expands the search for habitable conditions beyond Earth. Some of these planets orbit stars tens or hundreds of light-years away, making detection a precision game. But JWST isn't just about images. Its spectroscopic instruments decode the composition, temperature, and motion of what it sees. That includes star-forming regions, dying stars, and the intergalactic medium. It reveals how galaxies enrich themselves with heavier elements and how that chemistry spreads. One major focus is dark matter and early structure formation. By mapping galaxy distribution at different epochs, JWST refines our understanding of how dark matter halos attract gas. It helps trace the assembly of cosmic structure starting from the smallest clumps. These insights feed into simulations and cosmological models. It can also test models of dark energy. By observing supernovae and galaxy clustering at early times, JWST contributes to measurements of the universe's expansion rate. These data complete those from other missions like Euclid and Roman, but with higher resolution and longer reach. Infrared also lets JWST observe cool objects, brown dwarfs, faint galaxies, and even rogue planets floating in space. This extends our census of cosmic bodies far beyond what optical telescopes can detect. In that sense, it completes an unseen layer of the universe's population map. Its sunshield and position at L2 keep it cold and stable, essential for infrared sensitivity. This engineering feat lets JWST observe the cosmos in pristine clarity. It's not just looking deeper, it's looking cleaner than anything before it. JWST doesn't replace Hubble, it extends its legacy. It's not just about pretty pictures, it's about redefining our timeline, questioning assumptions, and offering tools to probe the invisible. That includes the mysteries of dark matter and dark energy, and the structure of everything that followed. What JWST sees may not just clarify the past, it may rewrite our entire understanding of the early universe. The final question: what if we're completely wrong? For decades, science has built a consistent model of the universe. It includes general relativity, quantum mechanics, and the standard model of cosmology. But 95% of the cosmos is made of things we've never detected directly. Dark matter and dark energy dominate, yet remain undefined. What if the entire model is flawed? The question isn't just philosophical, it's practical. If dark matter isn't made of particles and dark energy isn't vacuum energy, then much of our interpretation of data could be misleading. We'd be fitting observations into the wrong framework. The math might work, but the meaning might be off. History shows this can happen. Before heliocentrism, astronomers used complex epicycles to explain planetary motion. The model matched observations, but the underlying structure was wrong. Today's dark sector might be our new epicycle, a workaround for something deeper we don't yet understand. Some physicists argue we're missing the forest for the trees, that our focus on particles, fields, and forces assumes too much about what space and time actually are.
Maybe the error isn't in matter or energy, but in the fabric they exist within. This would require rethinking gravity, quantum fields, or both. Alternatives have been proposed. Some suggest dark matter is an emergent phenomenon, not a particle, but a manifestation of space-time geometry. Others say dark energy might arise from entropy, topology, or quantum fluctuations we don't fully understand. Each option demands radical redefinition of core principles. Another issue is the tension between cosmic measurements. The local expansion rate, Hubble constant, differs depending on how you measure it. JWST and other tools may increase this tension. If the mismatch holds, it could signal new physics or flaws in current assumptions. We also assume the laws of physics are the same everywhere, but what if they change over time or across space? Some theories allow for varying constants, like the fine structure constant or gravity's strength. If true, dark energy might not be a thing, just a symptom of shifting laws. Then there's the possibility that our universe is part of a multiverse, each with different physics. In that case, dark energy's value may be a random accident, one that just happens to allow galaxies and life. This anthropic argument doesn't explain how it works, only why we observe it. Quantum gravity remains unsolved. Until we merge general relativity and quantum mechanics, any cosmic theory is incomplete. It's like trying to explain a puzzle with half the pieces. Dark matter and dark energy may be cracks in the wall that revealed the missing theory, but we don't know how to read them yet. So what if we're wrong? Then the challenge isn't to discard what we know, but to ask better questions, design better instruments, and accept uncertainty. Science advances by confronting its limits, not hiding them. Dark matter, dark energy, expansion, structure, all may need reinterpretation. But the mystery isn't failure. It's a signal that something deeper is waiting to be uncovered. The difference between invisible and non-existent. What are we really looking for? In science, not seeing something doesn't mean it's not there. Some of the most important forces in the universe, gravity, electromagnetism, are invisible to the eye. We detect them by their effects, not their appearance. Dark matter and dark energy fall into this same category. They are inferred, not observed. But that raises a critical question. Are we chasing things that are truly invisible or things that don't exist at all? The line between these two is thin and depends entirely on how we define evidence. Just because something explains data doesn't mean it's real. It might just be the best placeholder we have. Dark matter, for instance, explains galaxy rotation curves, lensing effects, and structure formation. But no direct detection has occurred. We've designed increasingly sensitive experiments, yet found nothing. So, is it invisible, or are we misreading the signs? Maybe the gravity itself behaves differently than we expect. The same applies to dark energy. It's invoked to explain why the universe's expansion is accelerating. But is there really a mysterious energy filling space? Or are we misunderstanding cosmic geometry, time, or the role of the quantum vacuum? The name dark energy describes our ignorance, not a confirmed entity. Physicists build models based on what works. If a concept predicts observations across multiple domains, like dark matter in galaxy dynamics and the cosmic microwave background, it gains traction. But a consistent model isn't proof of existence. Epicycles once explained planetary motion too, until a better theory came along. We often confuse undetectable with non-interacting, but the universe might contain components that do interact, just not in ways we've thought to measure. Maybe we're using the wrong instruments, or looking for the wrong signatures. The signal could be there, just encoded in unfamiliar language.
Some theories suggest we may be detecting artifacts of hidden dimensions or fields. In those cases, what we interpret as dark matter might not be matter at all, but a manifestation of how space-time curves or evolves. Invisibility here would be a property of the framework itself, not of some missing substance. There's also the problem of human bias. We expect the universe to be made of things, particles, forces, energies. But nature doesn't owe us such clean categories. It might be that what we call dark is not a thing, but a behavior, an emergent pattern, not a substance. This leads to a deeper question. Are we asking the right questions? Our models reflect our instruments, our math, and our assumptions. If the invisible remains silent, maybe it's because our framework is too narrow. We might be trying to force-fit reality into a box that simply doesn't fit. Still, there's a difference between lack of observation and proof of absence. The fact that dark matter and dark energy explain so much, yet resist direct detection, keeps them in the invisible but likely real category. But as our tools improve, that boundary may shift. We might discover that both are real, just very elusive. Or we might find out we've been chasing ghosts. Either way, science progresses. The key is to keep testing, questioning, and refining. Invisible doesn't mean imaginary, but it doesn't mean true either. Until we see more clearly, the universe keeps its secrets, and we keep asking, are we missing something invisible, or are we misunderstanding something that isn't there at all?